Visualization of geological outcrops, which involves creating virtual 3D models, plays a vital role in geoscience. Often, manual visualization via a piloted aerial robot is preferred over airborne laser scanning. However, there are several challenges that include flights over straight path results in blurred images due to consistent camera focusing. Then, maintaining a specific overlap is difficult in windy environments. Besides, the pilot must continuously steer to always face the outcrop. Moreover, hiring a skilled pilot gets expensive for hours of data collection process. Therefore, we propose a fully autonomous visualization solution in this work. There are two aspects to the proposed visualization solution. The first aspect is the navigation algorithm that generates a suitable mapping path while maintaining a specific distance to the outcrop. This circumvents the continuous autofocusing requirement, thereby resulting in consistent quality images. Additionally, the navigation algorithm also commands the yaw angle such that the robot always faces the outcrop. As the second aspect, we incorporate a non-linear model predictive controller in conjunction with a Gaussian process-based regression technique to precisely track the generated trajectory in the presence of wind disturbances. Thanks to the accurate learning of disturbance forces by the GP, a substantial improvement in the tracking performance of conventional NMPC is realized. In terms of the control framework, we design NMPC as a high-level position controller that takes the trajectory reference from the navigation algorithm. By solving the formulated optimal control problem, NMPC commands the attitude angles and throttle to the low-level controller performing the attitude control. This results in the conventional NMPC-based position control, which is unfortunately sensitive to the uncertainties. Hence, we utilize a GP model that learns the external disturbances acting on the robot and thus making NMPC adaptive to the changing environment. Furthermore, the accurate learning ability of the designed GP model is mainly credited to the long short-term memory feature. In a sense, each GP model consists of two sub-GP models. The first sub-GP model is designed with the data collected for the first 15 seconds and thus represents the long-term memory. The second sub-GP model, on the other hand, is designed based on the data collected over a past window with 200 samples. Additionally, this window moves forward in time, thus granting it the short-term memory feature. Finally, the overall GP model is constructed by concatenating the two sub-GP models. Now, to conduct the offshore visualization, an off-the-shelf quadrotor platform, DJI Matrice 100, is utilized with certain modifications. Most importantly, its flight controller is replaced with the Pixhawk flight controller to command it in the ROS environment. Besides, sensors including RTK GPS, LiDAR light, and PX4 flow are added for precise outdoor localization. Additionally, 3 Terra Ranger distance sensors are mounted, which besides providing the feedback for wall distance, also facilitate computation for the desired yaw angle. Furthermore, the robot houses an NVIDIA Jetson TX2 onboard computer to run the control codes. We first evaluate the performance of the learning framework in the gazebo-based simulation environment of the outcrop, wherein the time-varying wind disturbances are introduced along X and Y directions. In the beginning, the robot flies with a conventional NMPC until the GP model gathers data to initialize its submodels. Once the GP model is initialized, it provides the learned disturbance forces to the NMPC. As can be seen, the Euclidean error is substantially reduced due to the GP-based learning. Next, we tested the algorithm in a chalk query located in Aalborg, Denmark. Again, the robot starts with conventional NMPC and switches to the GP-NMPC framework after the GP model gathers the required data. The real-world tests also exhibited an improvement in the tracking performance of NMPC due to the GP-based disturbance learning. Moreover, the robot is seen to accurately track the trajectory command from the navigation algorithm. For more details, please refer to the paper.